Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription really makes a difference and helps this channel grow. If you enjoy our content and don't want to miss upcoming videos, subscribe to the channel and activate the bell to receive all notifications. Pulsars are among the most fascinating and complex objects in modern astrophysics, phenomena born from the gravitational collapse of massive stars that, at the end of their life cycle, explode as supernovae, leaving behind a neutron star. An extremely dense body, where masses equal to that of the Sun are concentrated in a sphere just a few kilometers in diameter. This collapse entails the conservation of angular momentum, resulting in the very rapid rotation of the residual star. Pulsars are particular neutron stars that emit beams of electromagnetic radiation, mainly radio waves, but also X-rays or gamma rays, along their magnetic axes, which are tilted relative to the rotation axis, creating an effect similar to a lighthouse that pulses with an extremely regular period corresponding to the rotation period. These radio pulses, recorded by terrestrial radio telescopes, are among the most precise signals in the observable universe and allow scientists to probe not only the properties of the neutron stars themselves but also to test theories of gravity, study the interstellar medium, and even search for gravitational waves. In most cases, pulsars rotate very rapidly, with periods ranging from a few milliseconds to a few seconds. The so-called millisecond pulsars, for example, can rotate more than 700 times per second, as in the case of pulsar PSR J1839-0756 AD, the fastest known. Such speeds fall within the theoretical framework of neutron star formation and their evolution through matter accretion from a binary companion, which acts as a spin-up, increasing the rotation frequency. The combination of an intense magnetic field and rapid rotation allows pulsars to emit very energetic and stable radio pulses. However, the recent discovery of ASCAP J1839-0756 by a team from the University of Sydney has challenged this established paradigm. This pulsar, characterized by an extremely slow rotation, with a period of about 6 hours and 30 minutes, represents an anomaly because, according to standard models, after a neutron star slows down beyond a certain period limit, its residual rotational energy would be insufficient to power the engine generating the radio pulses. In other words, it was assumed that neutron stars with such slow rotation would be in a pulsar death state, unable to produce observable emissions. The fact that ASCAP J1839-0756 still emits regular and defined pulses has thus put many current theories about pulsar radio emission into question. The confirmation of this very slow rotation was made possible thanks to the use of several radio telescopes, including the Australian Square Kilometre Array Pathfinder, ASCAP, Meerkat in South Africa, and the Australia Telescope Compact Array. These instruments allowed observation of the radio emission at different frequencies and with high sensitivity, confirming the long periodicity and the characteristic double peak in the signal, a phenomenon known as interpulse, typical of pulsars in which the magnetic and rotation poles are almost perpendicular. This suggests that we are observing emission coming alternately from both magnetic poles, a fact that makes the origin of these pulses in such a slow pulsar even more intriguing. Several hypotheses have been proposed to explain the nature of this ultra-slow pulsar, each with deep and potentially revolutionary implications. One main hypothesis is that ASCAP J1839-0756 might be a magnetar, i.e., a neutron star with a magnetic field enormously more intense than that of normal pulsars, on the order of 10 to the power of 14 10 to the power of 15 Gauss, up to 1,000 times stronger than Earth's magnetic field. Magnetars are known for emitting powerful X-rays and gamma rays and having slower rotations than standard pulsars, but until now they had never been observed with such long periods in radio emission. The possibility that a magnetar can emit radio pulses at such low frequencies suggests new particle acceleration mechanisms and magnetospheric interactions not yet understood and requires updating stellar magnetosphere theoretical models. Moreover, this hypothesis links to recent observations of magnetars that also emit transient radio waves, as in the case of XTE J1810-197, but with much shorter periods and more intermittent emissions compared to the stability observed in ASCAP J18390756. Another very intriguing and highly speculative possibility is that ASCAP J18390756 is not a neutron star but a particularly compact, slowly rotating magnetic white dwarf, an object where density and magnetic properties reach extreme but lower values than neutron stars. White dwarfs are the evolutionary remnants of lower mass stars and are generally much larger, thousands of kilometers in diameter, and less dense than neutron stars. However, some white dwarfs with high magnetic fields have been discovered, and recent observations have shown some variable radio emissions from white dwarfs, although not yet pulsating with the regularity of pulsars. If this hypothesis were confirmed, it would open new scenarios on how white dwarfs can generate coherent and pulsating magnetic emissions, perhaps through interactions with stellar companions or residual accretion disks, or even through magneto-rotational mechanisms not yet described. This could indicate an evolutionary continuity or overlap between objects previously classified distinctly as neutron stars or white dwarfs. Another aspect that has attracted attention concerns the slowing down process of the pulsar. Such slow rotation implies that the neutron star has lost an enormous amount of rotational energy over time. This slowdown could have been favored by intense emission of magnetic wind or interactions with a plasma-rich surrounding environment, perhaps a remnant of material expelled by the star during the supernova or from an undetected binary companion. Alternatively, some theories suggest that a catastrophic event, such as a glitch, reverse, a sudden slowdown instead of an increase in rotation speed, or the accumulation of matter on a magnetically active surface, could have caused an almost total stop of the rotation. The result is a nearly hibernating star, still capable of emitting radio pulses but much less energetic than fast pulsars. These scenarios offer interesting avenues of research for magneto-rotational dynamics and the evolution of compact stars over time. In the context of neutron stars, there are already examples of extreme objects showing unique characteristics. For instance, the millisecond pulsar PSR J17482446 AD rotates at an incredible speed of 716 rotations per second and is in a very compact binary system. This neutron star, besides rotating rapidly, is also a natural laboratory for accretion processes that produce intense X-ray flares and for tests of high-energy physics and general relativity. The comparison with ASCAP J18390756, the ultra-slow pulsar, highlights the extraordinary diversity of physical conditions and possible evolutions for these objects, emphasizing the need for more flexible and comprehensive theories. The discovery of ASCAP J18390756 also has important implications for future searches of long-period pulsars, a potentially numerous population but so far almost invisible due to technological and methodological limits. Standard search techniques favor the detection of fast and regular repetitive signals, while very slow signals require prolonged observations, high sensitivity, and sophisticated data processing algorithms to be isolated from background noise. If this ultra-slow pulsar is an example of a so far hidden class of objects, their study could revolutionize our understanding of the neutron star population and their evolution in the cosmos. From a theoretical point of view, the presence of ultra-slow pulsars with stable radio emissions opens the possibility that some physical mechanisms, such as interaction between magnetic field and plasma, or the presence of superconductive or superfluid internal layers, may play a key role in maintaining emission at longer periods than previously thought. New forms of energy dissipation, Alvin wave emission, or particle acceleration processes in magnetospheres with very particular configurations could also be involved. All this pushes scientists to develop more sophisticated models integrating quantum, relativistic, and magnetohydrodynamic phenomena in extreme regimes. Finally, the discovery suggests that the boundary between neutron stars, magnetars, magnetic white dwarfs, and other compact objects may be more blurred than previously assumed, with possible hybrid or transitional categories escaping traditional classification. Future research, both through deeper and broader spectrum observations and advanced theoretical experiments and simulations, could lead to a radical rethink of high-energy physics, dense matter, and magnetic phenomena in astrophysics. In conclusion, ASCAP J1839-0756 is not only an ultra-slow pulsar but a true challenge to current models, an invitation to review the physical laws governing compact stars, and a potential beacon for new discoveries in the vast and still largely mysterious universe of neutron stars and their enigmatic cousins.